Welcome back to our continuing series of the videos here of the practical exercises. This particular one we're going to go through the series parallel circuit, skill practice 13. Now the circuit, as per your module books here, is a series parallel combination. We've got resistors in series, a parallel combination, another resistor in series with a supply. What I've done, I've pre-drawn that for you. So the first thing we'll have a look at are the values throughout the circuit. We've got a supply voltage of 18 volts into a switch, into resistor R1, which is an 18 ohm, goes into a parallel combination of 150 ohm with a 56 ohm resistor, so R2 and R3. They combine into another series resistor of R4, 33 ohm, back to home. Now I've purposely drawn the supply that's positive there and negative there. Doesn't matter which way it goes, current and voltage, it's still going to add up. So we're going to confirm a couple of our rules that we've learnt previously or discussed in class. Kirchhoff's voltage law, which states the sum of the voltages around a series circuit add up to the supply voltage. So this voltage plus the voltage across the parallel combination plus this voltage here across R4 will add up to equal the supply voltage of 18 volts. The other thing, Kirchhoff's current law said the sum of currents entering a junction is equal to the sum of the currents leaving the junction. So this current here will be the supply current. That current will split into two. One current will go down to this 150 ohm, one current will go down to 56 ohm. Those two currents will combine at this junction here and equal the supply current again, which will go back to the supply. So the first thing we need to do is calculate the equivalent resistance of this parallel combination. Once we calculate the equivalent resistance, we can add the three resistors up like a simple series circuit. Now we've got a 56 ohm in parallel with 150 ohm. Our theory has taught us that the parallel resistance is going to be less than the lowest value resistor. So in this particular case, the lower value resistor is 56 ohm, so the equivalent resistance is going to be something less than 56 ohm. Let's have a look. So Req is equal to 1 on 150 plus 1 on 56, and that's actually 1 on Req, of course. Okay, is equal to, so we'll go over to our calculator, 150 inverse plus 56 inverse equals that inverse equals 40.77 ohms. So Req is equal to 40.7, we'll call it 8 ohms. So we can write that value in and the RE equivalent. So that resistor is a 40.78 ohm equivalent resistance. Once we know that, we can add this resistance, R1 plus the equivalent resistance plus R4 to have the total resistance. Total is equal to 18 plus 40.78 plus 33. We've already got that in the calculator there, so we're at plus 18 plus 33. 91.78 ohms is equal to 91.78 ohms. That's the total resistance. Now once we know the total resistance of this circuit, we can work out the total current flowing through the circuit. As per our Ohm's law, cover up the I is equal to V over R. So total current, right, IT is equal to V over R, which is equal to 18 volts divided by total resistance, 91.78. Is equal to, that's R, just make that, it's RT. Okay, so it's 18 divided by 91.78 is equal to 0.196 of an amp. 0.196 of an amp, or as we know, it's count 3 to the right hand side, 196 milliamps. It's IT. Now that current that I've calculated there will be the current flowing through R1, it'll be the current flowing through R4, or current anywhere along this path. So we'll check that when we go to wire it up. Next thing we want to work out is the current through this equivalent branch here. So we know that there's 196 milliamps flowing through this parallel circuit. Obviously some breaks off through that resistor, some breaks off through that resistor. So the next thing we've got to work out is what is the voltage drop across this parallel branch. Ohm's law, cover up V. V is equal to I times R. So VR equivalent, VREQ, is equal to the current, which is 0.196, times the equivalent resistance of 40.78, is equal to, I've already got it in the calculator, 0.196 times the equivalent resistance, 40.78, is equal to 7.99 volts. That's the voltage drop across this equivalent branch. So I'll do a little voltmeter. Down here. Go across like that. So the voltage we're expecting to see across this parallel branch is around 8 volts. Keep it simple. We'll say 8 volts. Now the other voltage drop, we've got another voltage drop across R1. Another voltage drop across R4. So that's V1. Another voltage drop across R4. So that's VEQ. So VR1 is equal to I. The current is 0.196 times the resistor of 18 is equal to 0.196 times 18 is equal to 3.53 volts. And VR4 is equal to 0.196 times the resistance of 33 ohms, 0.196 times 33 is equal to 6.47 volts. Now, is that all the calculations? Let's have a look. We've got the voltage across R1 because we want to confirm these readings, these theoretical calculations with the circuit. So I've got the voltage across R1. I've got the voltage drop across the equivalent branch resistance, which would be 8 volts. It would also be obviously 8 volts across this same one because it's the same voltage drop across parallel branches. 8 volts, same 8 volts. And then third voltage drop across VR4. So simply put, it's that voltage plus that voltage plus that voltage is equal to the supply voltage. I think I'm missing something. And I am. I'm missing the current that's flowing through this resistor and the current flowing through that resistor. The currents will be different. So let's have a look at working out the current through IR2. So IR2 is equal to V, okay, across that resistor, so VR2 divided by that resistor, 150 ohm. So R2 is equal to the voltage drop across that resistor is 7.99, but let's round it up to 8. 8 divided by 150 is equal to, let's have a look here, 8 divided by 150, 0.05 of an amp. Okay, and the current through IR3 is equal to VR3 divided by R3, which the VR3 is the same 8 volts, so 8 volts divided by the resistance 56 ohm. And as we know from our theory, that current takes the path of least resistance, so therefore we're going to have a higher current through the 56 ohm. Is that true? It is. 0.14 of an amp, 143 of an amp for that one. Over that one and that one. So that's our calculations. Supply voltage of 18 volts, series parallel combination circuit. So what I've done, I've pre-wired that circuit. So now we're going to confirm this theoretical calculation and see if it works in the practical world. Okay. I'll turn the circuit on. So the first thing we've got here, we've got the switch, goes into the ammeter, and this ammeter goes into the first resistor, which is R1. So the ammeter is reading 0.196 of an amp, which is our supply current. After that resistor, R1, then the circuit goes into the parallel combination of a 150 ohm and a 56 ohm resistor. Parallel combination. So it comes in these two resistors are in parallel. Out of these two resistors, they combine through 2 ammeters back to them. So we'll have a look at the first resistor, which is R2. So it comes into R2, current goes through R2, into an ammeter, out, back into the resistor. So the value there of IR2, as you can see, is 0.054 of an amp. And we move over to the other parallel combination of IR3. So the current, once again, goes through IR3 into an amp meter and out, so back into the common junction. So the current through IR3 is 0.142 of an amp. And those two currents combined, the sum of those two currents combined, go through the 33 ohm, which is the R4 resistor, and back to the negative of the power supply. The other thing we're going to have a look at is the voltage drops across the circuit. And to see this voltage drop plus this voltage drop across this parallel combination plus this voltage drop should equal the supply voltage, which is what we've calculated. So the first voltage drop we'll have a look at is the voltage drop across R1. So voltage drop there, 3.47. Now we'll have a look at the voltage drop across the parallel combination. So I'm going to go across the 56 ohm, which in this particular case is R3, and that's 7.98 of a volt. Or the voltage drop across 150 ohm, which is R2, it should be the same value, which it is, 7.98 volts. And the last voltage drop is the voltage drop across R4, which will be, as calculated, 6.5 volts. And as our theory tells us, we'll just scan back to the calculations to confirm with the calculator. Let's have a look. VR1, 3.53 plus voltage drop across the equivalent resistance, 7.99, plus the voltage drop across R4, 6.47, is equal to 17.99 volts. So nigh on perfect, coupled with the fact that all these readings were pretty close to what we achieved once we wired the circuit. And thus concludes the series parallel practical combination.